for your excellent talk again. We are going to move to the next talk, which is Lara Anderson. Lara, could you please share your screen?
Thank you very much.
Does that look okay?
Please.
Well, first, let me say thank you very much for the organizers to the opportunity to join. I have really enjoyed the talks that I've heard so far this week, and I'm really blown away by the diversity of topics that are being explored. I want to also say thank you to Challenger. I'm benefiting from this order of talks because I'm going to mention some of the things that the Challenger introduced very nicely, so I can do those more briefly, thanks to this ordering. So I'm going to be talking a little bit about some work that appeared around the same time as the work that Challenger was describing last December on machine learning approaches to Calabi-Yau and SE3 structure metrics. I'm only going to touch on this sort of schematically with the core ideas. Fabian will be giving a talk, I believe, later this afternoon that is going to look at more of the details of that. And I'm going to talk a little bit about some extensions of this work that are aiming towards completing this to Hermitianing those connections on stable bundles in the context of heterotic compactifications. And I'd just like to shout out at the start to some of my collaborators, in particular on the machine learning work. I want to flag the important programs of research by both Sven and Fabian. This was me dipping a toe into machine learning for the first time, but these two gentlemen both have major programs pushing this forward, which I think is great. In the work in progress that I'm going to be talking about, including work on stable bundles, I also want to flag my two collaborators, three actually at Virginia Tech, James Gray, long-term collaborator, and we are currently working with two undergraduate students, Dylan Bloodworth and Nathan Tompkins. Normally we do not work with undergrads on our projects because they're just not an appropriate level, but we were fortunate to get two really exceptional undergrad students. And I just want to flag the fact that both of them are applying to grad school at the moment. So if you're looking for really first-rate students, consider those guys. All right, with that in hand, let's dive right in. So Challenger gave some very nice general motivations for some of the questions in the context of string compactifications for considering machine learning techniques to study both metrics and gauge connections. So I want to focus in my talk primarily on heterotic compactifications as an application of these tools, although of course they're much broader. So the target that has been viewed as a target for numeric approximations of metrics and connections has been for many years to understand more detailed properties of heterotic effective theories, n=1 theories in 4 dimensions. So for example, Yukawa couplings in heterotic string theory in the n=1 superpotential descend from a 10-dimensional action term of the form given here, which manifestly depends on the metric on the full 10-dimensional space and hence on any compact directions that you have in the game. In addition, if you're starting with a gauge field in 10 dimensions, you must define a perturbative theory around a background in which you specify gauge field vevs over those compact extra dimensions. And you can consider perturbations around that background, which will be parameterized by harmonic one forms, the coefficients of which will be 4D scalar fields. In general, the superpotential trilinear couplings are given by an integral over the compact directions, something of this form, a set of harmonic one forms wedged together with a holomorphic 3 form. And of course, the normalization of such a term is manifestly going to depend on the metric for the space. Now, from a physics motivation point of view, why do you care? We are interested in lots of details of n=1 theories in 4 dimensions. So from a model building string pheno point of view, the particle masses and couplings, questions like what is the mass of the electron in your vacuum is not something that you can answer without control over something like the metric. Questions about hierarchies and textures, whether you have a heavy top quark in supersymmetric theories, which of course we're considering, the mu problem, asking whether you can forbid rapid proton decay operators. Lots of these things actually involve understanding couplings and their normalization. Importantly, through the matter field Kähler potential, which is completely unknown in the heterotic case. And this is a major pain in terms of specifying effective theories for many, many years. In particular, this matter field Kähler potential manifestly includes a Hodge star, which again is bringing metric dependence into this problem. Now, I want to begin by considering the easiest class of solutions, which Challenger's already touched on, which is the case that beginning in a 10-dimensional theory and reducing down to 4, we have X as a complex 3-dimensional or real 6-dimensional space. And I will choose it to be a complex Kähler manifold that is admitting a Ricci flat metric, i.e. a Calabi-Yau manifold. And the major open question here is how to determine the metric and connection, and was already pointed out in the last talk. There are no general analytic tools for metrics on Calabi-Yau threefolds. So the current viable approach is numeric approximation. Now, there's a long history to this that's been going on for over 10 years in terms of using existing numeric schemes to try and approximate the metric. I won't go into huge details of these, but I want to just give a flavor for some of the ideas because they'll be important later in the talk for other applications. So in particular, the basic handle that has been employed, I would say the last decade or so to try and approximate Calabi-Yau metrics has been to use some simple metrics that can be parametrically tuned to a Ricci flat solution. So you have to ask, where am I going to get my hands on a set of very explicit, very simple metrics that I can use to approximate Calabi-Yaus? And the answer is through projective embedding, so the so-called Kodaira embedding. So given an ample line bundle on a Calabi-Yau, then there exists an embedding into some sufficiently large complex projective space where the mapping exists through the global sections of this line bundle. In general, not all line bundles have global sections, so we'll consider if, well, we're considering an ample line bundle so that it does, and then we'll consider high twists of it to generate enough global sections to have a good embedding. The reason that this is a nice approach is that on CPN, you could come with a very easy, explicit natural Kähler metric, the so-called Fubini-Studi metric, which can be written in the simplest case as log mod z squared and can be generalized to include a Hermitian matrix Hij bar. In general, Hij bar must be non-singular and Hermitian. You can then pull back the Fubini-Studi metric to your Calabi-Yau, and this will not be Ricci flat. It wasn't Ricci flat on CPN because this is not a space that admits a Ricci flat metric, and it will not restrict to one on the Calabi-Yau. However, there's some nice structure that allows one to actually use it to come up with an approximation scheme. And this was results due to Donaldson that really established this. So in particular, you can show that Kähler potentials of the form that I wrote down here for a complex Kähler manifold are actually dense in the moduli space. This is a result due to Tian. And so the idea behind an algorithm developed by Donaldson was that you can sort of parameterize all infinitesimal paths in metric moduli space using Kähler potentials of this form. And Donaldson introduced the notion of a T operator and equivalently the notion of a balanced metric. Basically, this is an iterative approach to stabilizing the form of these H's such that you have good asymptotic behavior as you increase the twist on K. That is very loose. I'm not going to get into the details of exactly how this works, but the punchline is that for each K greater than 1, if you have a specially chosen balanced metric on this Hermitian line bundle, rather a Hermitian fiber metric on this line bundle, it will exist and is unique. And then as an iterative sequence, as I increase K to infinity, this will converge to a Ricci flat metric for the given Kähler and complex structure. So this gives you a controlled approximation scheme. If you ran it to infinite K, this would be exact. Of course, you're not going to do that. But to finite K, you have good computational control over being able to guarantee that there's a convergence of the form you want in metric space. The approach this approach, as I sketched it, was implemented over 10 years ago by Douglas and company over at all. I worked on this with Bert and collaborators in the context of connections. And this works. You can actually numerically implement Donaldson's algorithm quite well. The problem is that it's very computationally intensive. Order days to weeks to produce a metric using existing numeric schemes at one point in moduli space. And it's an important question whenever you're working on numerics to ask, is this, if you went to the trouble of doing a numeric implementation, is this actually accurate enough? The hard part is we don't really know because this was so difficult to compute that no one had actually pushed the computation all the way through to the physical quantities that I mentioned at the beginning that were motivating this work. So really computing a matter field Kähler potential, really normalizing fields, studying string vacua. You don't quite know what the necessary accuracy on a metric is until you've pushed that computation all the way through, and just all the steps were too computationally difficult to do that. So with the advent of machine learning techniques entering into string theory, as Challenger outlined, this is an opportunity to say, can we optimize these numeric approaches? Can we use the Donaldson algorithm or something completely different to attempt to just make this faster and more efficient? So in this first paper with Sven, James, Fabian, and collaborators, what we considered was several different experiments. The first is supervised learning of the moduli dependence of Calabi-Yau metrics using the Donaldson algorithm to generate trading data. And the goal here was really to bypass this downside of existing implementations of the Donaldson algorithm that they only worked at one point in moduli space. We also, very similarly to the work that Challenger outlined, we considered direct learning of moduli-dependent Calabi-Yau metrics, both using the metric ansatz, the same one that Donaldson used, and without it. And then importantly, in my view, we considered generalizations of this away from the Kähler context into more general SU3 structure manifolds with torsion. Now, I don't have very much time, so I'll give just a brief flavor of these results. As was also highlighted in Challenger's talk, the work that I'm describing here appeared at the same time as work by Douglas and collaborators and also Jajala and collaborators. Also, you'll hear more refinements of these ideas and a very cool implementation in a package in talks of Fabian and Robin later in this workshop. So preliminaries, one definition of a Calabi-Yau threefold is that we can define it in terms of simple structures that exist on such a manifold. Namely, it is a complex threefold emitting a nowhere vanishing two form and a complex three form, J and omega respectively, that satisfy certain multiplicative and differential conditions. These two being the multiplicative ones and the condition dj equals 0, obviously, that this is a Kähler manifold and that the holomorphic three form is closed. An example that is the simplest one to start with, and hence we all did, is the quintic hypersurface in the CP4. I'll consider a deformed Fermat quintic of this type. Importantly, for the work I'm about to describe, the holomorphic three form can actually be explicitly constructed in terms of the description of this algebraic description of the manifold as a hypersurface inside a Calabi-Yau, as was pointed out by Candelas and collaborators. So the first is direct learning of the Kähler potential. So the balanced metric that's output by Donaldson's algorithm at a given finite K, this twist of a line bundle, is not necessarily the most accurate approximation to the Ricci flat metric. And the question is, for finite K, can you actually come up with an approximation scheme that does better, perhaps? We generated networks to find parameters that are trained directly to use such a loss, and we've referred to this as the Monge-Ampere loss. This is the same one that appeared in Challenger's talk. This quantity should go to 0 if the J and omega satisfy the conditions that I had on my previous slide. I should note that minimizing a loss function of this type is not a new idea. This was pioneered by Hedrick and Nassar. The difference in their case is that they considered minimization problems using built-in packages in Mathematica to try and tune to a Ricci flat metric. Here we're using neural networks and machine learning. I'll skip over the network architecture because I believe more of that is going to be discussed in the next talk. But let me give a flavor of some of our results. So these initial networks were optimized for a range of complex structures, modulo psi between 0 and 10. And the flavor of the results is given here. You can see the shaded regions are the actual output of our neural networks. And we're comparing them to the dotted line, which is Donaldson's algorithm at k equals 6. The two plots here are just different ranges of the complex structure. The sort of clear region of the plot is the actual generated data and then extrapolation to higher complex structure. So the takeaways from this first study are that the Donaldson algorithm with k equals 12 takes order days to run or longer, depending on the manifold, even for the single case of psi equals 0 on the quintic. This metric at this network at k equals 6 takes only minutes and gives comparable accuracy for a very wide range of complex structure. We can do better than the Donaldson algorithm at k equals 6, and this improvement actually extends to quite high complex structure, nearly a factor of 2 beyond the regime used during training. So these are promising initial results. In addition, we also could consider direct learning of the metric. Rather than using the ansatz for the Kähler potential employed in the Donaldson algorithm, you can ask, can I try and learn the Calabi-Yau metric directly? It's fair to ask, why do this? If you have a good ansatz, why drop it? The questions we wanted to ask were, perhaps we could improve performance by not being tied to an ansatz for fixed k. And most importantly, in my view, we'll be able to generalize this approach to more complicated geometries, namely away from the Calabi-Yau context. The disadvantage to that is if you drop the ansatz of Donaldson, then you actually need to check explicitly more features of the geometry to guarantee that you're ending up with a correct solution. And this was already discussed by Challenger. So the loss function, very similarly to the previous talk, is built as a composition of the Monge-Ampere loss. Now one has to check explicitly that the Kähler form is indeed closed, and the network is trained and run over different patches of the complex manifold. And here you have to implicitly or explicitly impose overlap conditions patch to patch to make sure consistency of the solution. Our input to this network were the real and imaginary parts of complex coordinates describing homogeneous points in the Calabi-Yau, and the real and imaginary parts of the complex structure. And our output was actually just directly components of the metric. To give a concrete example, we optimized at psi equals 10 on a data set of 10,000 points, split according to test train 90-10 and iterated for 20 epochs. Again, we see accuracy reaches the same level as Donaldson algorithm at k=5, and I believe this is readily improved and has been done so in the recent package by Fabian and collaborators. In the plots at the bottom here, we ran various experiments to sort of see how sensitive is this algorithm to the various elements of the loss function that I outlined before. So for example, you can ask, what does the loss look like? That's the red dots here, with all three elements of the loss function imposed, and you can begin to drop different pieces and see how does the system respond. So what is the most sensitive effects? At the right here, you can see that dropping the overlaps does effectively nothing, the overlap condition. And this is because morally the patch by patch solution is protecting itself against this kind of higher codimensional constraint. So this is not to claim it's totally safe to drop it, but it's not the dominant effect in terms of training the solution. On the other hand, without the Kähler condition, you're clearly, your loss is not going to converge rapidly. However, the Monge-Ampere loss is still doing something, and it's still heading downwards to some extent. So this leads naturally into the question, what is it heading towards? And that takes us to the final thing that I want to mention in the metric section of my talk, which is, can we generalize this direct learning of the metric away from the Calabi-Yau context? In particular, we were interested in studying SU3 structure manifolds. These are 6 manifolds that have, again, a 2-form and a 3-form J and omega that obey the same algebraic properties as the Calabi-Yau case, but have different differential properties. In particular, instead of being closed, the dj and d omega can be parameterized in terms of the so-called torsion classes, W1 through W5, where these are defined as explicit contractions of j and omega, as given here. Different string theories place different constraints on what torsion classes are possible. I'm going to focus here on the heterotic string, which has this particular conditions on the torsion classes for the Hull-Strominger solution. And this is the general n=1 solution in 4 dimensions. Note that the Calabi-Yau structure is a special case. In order to actually run a neural network, though, you could say, here's the torsion classes I'm aiming for. You could set up a big composite loss function and just let the whole thing loose. But you have the problem of, do you actually trust whatever it is you're getting in the case of SU3 structure? Because we have no existence theorems like you do in the Calabi-Yau case due to Yau. We wanted to begin by hunting for a solution that we knew existed. So in particular, we took very nice work by Larfors, Lucas, and Rula, who had shown that some Calabi-Yau manifolds admit not only Ricci flat metrics, but other nice SU3 structures as well. And so this group wrote down a nice explicit ansatz and solution for the Strominger system over a topological Calabi-Yau, but with a non-Ricci flat solution. So effectively, we trained a neural network to see if it could find this solution. And indeed, we find that it does. It converges quite reasonably. This is the first sort of dipping a toe in this direction. Obviously, you want to be able to hunt for solutions you don't know. You want to be able to use this more robustly. But I think this is a very nice indication that these tools might be very utile indeed in terms of hunting for these solutions, or even generalizing to odd dimensional manifolds like G2 or spin 7. For my remaining 5 minutes, let me now sketch what it is that we're trying with connections. So in the heterotic context, which is where I focused for the majority of this talk, it's natural to ask how much of this approach can be readily applied to gauge fields over the Calabi-Yau as well, i.e. to the Hermitian-Yang-Mills connections. So as a reminder, the Hermitian-Yang-Mills equations are the ones here. The 1-1 contraction of the metric and field strength of a non-abelian gauge bundle has to be equal to the slope times 1. For the case of heterotic compactifications, this is 0. So it's actually this thing vanishing. For stable bundles, you can encode the information in the connection in a so-called Hermitian structure or a fiber metric, from which you can explicitly build a connection. If you have a fiber metric that obeys this condition, G is called Hermite-Einstein. And importantly, it produces an inner product on sections of the bundle. This technology has actually already been employed in the Donaldson algorithm to compute the Calabi-Yau metric, in that there, morally, what you're doing is finding Hermitian fiber structures on line bundles. And all we have to do in this context is to try and generalize that. So we want to generalize the line bundle algorithm that is Donaldson to a rank n vector bundle. This was done in work by myself, Volker Braun and Bert Overt about 10 years ago in terms of just implementing a numeric implementation of the Donaldson algorithm. Since I'm running short on time, let me not get into huge details of what this generalized algorithm looks like. Here, essentially, again, you're using projective embeddings, using global sections now of a non-abelian bundle in order to construct a connection. There's a generalization of the T operator. And let me just fast forward to the punchline for this sort of generalized Donaldson algorithm. There's a theorem due to Wang that says, just like in the Donaldson case, there is a guaranteed convergence theorem for Hermite-Einstein fiber metrics, given the ansatz of the type that I'm describing. So there's a natural integrated error measure. This can be implemented numerically using a neural network, however you like. I should say that first steps in this direction have been taken by Yang and Anthony and Bert in recent work for applying this in the abelian case as well. So there's a generalization of Donaldson that applies to bundles. In my remaining 2 slides, oh yeah, here's what it looks like from 10 years ago. This is the kind of convergence for a stable bundle that you can see for the Hermitian-Yang-Mills connection. But in my last 2 minutes, what I want to highlight is a better way, perhaps, to actually apply this rather than the direct Donaldson algorithm. So in work with our students here at VT, James and I were interested in the question of, is there a more efficient way using neural networks or otherwise to try and compute a metric and connection in the heterotic context in one step effectively? So rather than compute the Calabi-Yau metric at a point in moduli space or for a range of moduli space, use that metric in the Hermitian-Yang-Mills connection in the Hermitian-Yang-Mills equation to then compute a connection using several iterations of neural networks. Could you effectively create one object that you could feed to a neural network and try and optimize in one step? So what's the basic idea? You want to create a composite metric on the total space of the bundle. This is a very old idea in physics that has come up in a lot of contexts. So morally, what would you expect? You have a total metric, G with capital indices, which looks like a part that is built out of a Calabi-Yau metric, a fiber metric, and then off-diagonal components that are effectively gauge fields. This should look familiar because this is effectively a Kaluza-Klein metric ansatz. This is different though, in that we're not doing Kaluza-Klein theory in the space-time directions. We're actually just trying to use a Kaluza-Klein type metric ansatz over the Calabi-Yau and bundle directions itself. So we want to ask, can we build a metric of this form that's encoded a connection and a Calabi-Yau metric directly into one object? And using exactly the same techniques for neural networks that I just outlined in the previous part of my talk, can we write down equations that this total object has to satisfy, write down loss functions that toggle to those, and then train a neural network to produce the whole thing in one step? There's a whole range of technicalities, and this is work in progress in terms of what exactly you choose for the total space and how you try and read off constraints and ingredients on the pieces. One choice that has been used in literature in some contexts is to write down metrics on the principal bundle itself, i.e. for SUN gauge symmetry, the compact fiber group would be a real manifold of dimension n²-1. The group manifold itself would be the fiber of the bundle. Alternatively, you can consider the projectivization of a vector bundle in some representation of the gauge group. So for example, in the way we normally build this, the vector bundle is defined in the fundamental representation. You can form the projectivization of this guy, and this will have fibers that are CPn-1. These are effectively equivalent information because the transition functions between principal bundles and vector bundles are the same, but just using different representations of the group to pull it off. A nice feature of projectivization of vector bundles is that they come equipped with canonical line bundles, which push forward on the base manifold to the original vector bundle you were projectivizing. In this context, there's some very nice properties known for the metric on the total space. In particular, there's a theorem due to Hong, which says that if the base admits a constant scalar curvature metric and the vector bundle is stable, i.e. it satisfies Hermitian-Yang-Mills, then the total space will admit a metric of constant scalar curvature. It won't be Ricci flat for the total space because you have compactified fiber directions with positive curvature, but you can still get it to be a constant. Effectively, this will live in a very obvious class, which is a Kähler form on the total space, which is built out of the field strength, the 1-1 part of the field strength, and the pullback of the Kähler form of the base. Obviously, to be of full interest for the context I described, this direction says, given a Calabi-Yau metric and a vector bundle connection, you could then build a metric on a total space. You want to be able to invert that and say, given a metric on the total space, can I pull it apart into the pieces that I want? And I won't get into the details of the mathematics literature on this, but there is uniqueness of this solution, and it is if and only if you can invert it in some circumstances, which can apply in the heterotic context. So the central idea that we've been exploring is, can we apply the Donaldson algorithm to Hermitian fiber metrics of this chosen line bundle on the projectivization? we can use a very similar machine learning implementation to the Calabi-Yau case, and then try and pull apart the metric and connection in one step. I should point out that one thing that is kind of cool about this approach is that an interesting extension is that the presence of generic Hermitian-Yang-Mills bundles that are not equal to the holomorphic tangent bundle actually deform the metric away from the Ricci flat solution, which is to say, in a heterotic solution at order, alpha prime is 0, have a Calabi-Yau solution, but once you add in the gauge fields at order alpha prime, you will have a non-Ricci flat solution for the gauge bundle. This is, of course, a Strominger system solution, i.e. back to SU3 structure. So another way of exploring what we've been exploring is, can we apply machine learning techniques directly to the vanishing of effectively the beta functions in this case, rather than solving for Calabi-Yau metric first and then Hermitian-Yang-Mills? So phrased differently, can we take the composite metric to actually tune itself to the full Hermitian-Yang-Mills SU3 structure solution at order alpha prime, rather than piece by piece? You could use similar approaches for non-Kähler metrics to what I described in the earlier part of my talk, the loss functions, misuse transition functions, etc. A question on this idea is, do you actually care? So you're going to get a correction, for example, to the Calabi-Yau condition that's order alpha prime, which you would assume is small. Where do you actually want that additional accuracy? And the main application from our point of view would be better control of the matter field Kähler potential, but it's not yet clear that actually this approach really buys you that much more. So this is an open question. I think that I am effectively out of time, so let me just conclude. The things that I very sketchily tried to outline for you today is that, as emphasized in the last talk as well, control of the metric is necessary in order to specify the 4D theory in a string compactification. Machine learning techniques have demonstrated through the work of a variety of groups and a variety of approaches that they can provide a powerful new tool in terms of advancing us towards this goal of better understanding of string effective field theories. In particular, in the work I outlined today, we provided the first numeric approximations to SU3 structure metrics, which I believe will be important for string pheno applications, including questions in moduli stabilization. We are currently exploring novel ways to package and then efficiently approximate the metric and connection data in a heterotic compactification. And there is a huge array of open questions, including pushing control of the heterotic effective theory further, matter field Kähler potentials, using this in moduli stabilization, etc. So with that, I will stop there.
Thank you very much, Lara, for a fascinating talk. We have 1 minute for 1 or 2 short questions. We can leave a longer question for discussion session. I'm sure we have more questions and discussion sessions. So let's move to the next